I'd like to start by defining acoustics. Acoustics is the science of sound, including its production, transmission, and effects. Applications of acoustics include medical ultrasonics, underwater acoustics, architectural acoustics, active or passive noise control, non-destructive evaluation, environmental noise, and many, many more. It is the application of environmental noise produced by highway traffic that will be discussed here, starting with the basics of sound. Understanding acoustics requires the understanding of sound. Sound is a vibratory disturbance created by a moving or vibrating source. As the source moves or vibrates, surrounding atoms or molecules are temporarily displaced from their normal configurations, thus forming a disturbance that moves away from the sound source. In order to better understand sound waves, it's first useful to study this animated representation of waves. In this demonstration, the sphere in the middle pulsates in and out at equal intervals, forming waves that propagate away from the sphere or the source. One way to picture this type of wave is by imagining yourself tapping your finger on the surface of water. As you tap, waves propagate away from your finger in a circular pattern. Now we're going to look at a snapshot in time of the wave animation in order to get a better understanding of wave parameters. For simplicity, the outward propagating waves can be approximated with a trigonometric sine function. The pattern of the sine wave repeats itself periodically. The wavelength of these waves, represented by the Greek letter lambda, is defined as the repetition length. As a wave propagates through an unchanging medium, its wavelength remains constant. Another parameter of a wave is its amplitude. The amplitude determines the strength of the wave. Greater disturbances at the source lead to greater strengths during propagation. For sound waves, a higher amplitude equates to a higher volume. Waves also have an associated frequency. Frequency, abbreviated with a lowercase f, is defined as the number of cycles of repetition per second. In other words, frequency is the number of wavelengths that have passed by a stationary point in 1 second's time. The unit of frequency used here is called hertz, abbreviated Hz. It's defined as the cycles of the wave per second. When the number of hertz exceeds 1000, it's common to write the amount in units of kilohertz. For example, 1000 hertz equals 1 kilohertz. Frequency is inversely proportional to wavelength. An equation relating the two parameters is C0 equals f lambda. C0 is the speed of sound in the medium. In air at a temperature of 20 degrees Celsius, the speed of sound is 343 meters per second. This equation implies that longer wavelengths are associated with lower frequencies, and shorter wavelengths are associated with higher frequencies. Sound can have a single frequency component, as we earlier illustrated. Or it can have multiple frequency components at varying amplitudes, thus making each sound distinctive. This type of sound is complex. Most real-life sounds are complex. For convenience, the frequency components of a complex sound source are very often studied in terms of octave or fractional octave bands. These bands each cover a range of frequencies and are referred to by the center frequency of the band. When a sound is complex, it can be called broadband because it encompasses many frequency bands. For octave band analysis, the entire frequency spectrum is divided into 1 octave bands. A list of these bands is shown in the table. The center frequency of each band is 1 octave higher than the previous band. Notice the center frequency's associated wavelengths. For the frequency of 31.5 Hz, the wavelength in air is 10.89 meters, or 35.72 feet, and for the frequency of 8,000 Hz, the wavelength is 0.04 meters, or 0.14 feet. We've used animation to help describe various wave parameters. Now that these parameters have been explained, let's look at a demonstration of how sound waves operate. Sound waves must propagate through some medium, since it's the medium's particles that support the wave. The example medium here is air. Now a source is introduced on the left side. It is producing a pure tone or single frequency sound wave in the air. The air particles are displaced as the waves propagate away from the source. The particles themselves are just oscillating back and forth, but it can be seen that the sound waves are propagating outward. As the air particles bunch up, this forms a high positive amplitude area, and when they are most spread apart, this forms an area of high negative amplitude. In their undisturbed configurations, the particles represent an area of zero amplitude. The amplitudes correspond to a change in pressure from its ambient value. This is termed the acoustic pressure. A sine wave is again shown to better understand the wave parameters. Notice how the darker areas of the acoustic wave line up with the peaks of the sine wave. We have now defined wave parameters, including frequency, and have illustrated the important characteristics of sound waves. The discussion has focused on the sound source. It's also important to understand the receiver of the sound. As an example, sound waves travel through the air and interact with the human ear. Perfect human hearing lies in the range of approximately 20 to 20,000 Hz. Frequencies below 20 Hz and above 20 kHz are heard by other living creatures but not by humans. 20 to 20,000 Hz is called the audible sound range. Infrasound includes frequencies below 20 Hz. And ultrasound includes frequencies above 20 kHz. In order to connect frequencies with sounds we recognize, let us first listen to the piano. A piano covers a frequency range of 55 to 8,360 Hz. A middle C is at 262 Hz. Human conversation is also recognizable. Nearly all information in human speech is contained in the frequency range of 200 to 6,000 Hz.
I've been for a number of years.
Oh, you've been to England often?
Years ago.
Uh-huh.
Some family from England.
It should also be noted that human hearing is most sensitive between about 1 and 6.3 kHz. Now that we better understand sound, it's suitable to introduce a more subjective part of sound, noise. Although sound can be measured as a physical quantity, noise requires the judgment of a human listener. Noise is defined as any unwanted sound. Unwanted sound may be defined differently depending on the listener. However, several types of noise are understood to be objectionable. These types include highway traffic. This type of noise will be discussed later in the presentation. Loud machinery or tools. And aircraft. A better understanding of noise involves quantifying its perception. Physical measurements of the strength of the wave are explained first, followed by perceptual measurements. We talked before about the amplitude of a wave. The amplitude of a sound wave can be quantified by measuring the associated pressure disturbance. In other words, we need to measure the change in pressure from its ambient value. Again, this change in pressure is termed the acoustic pressure. Sound can be represented in terms of a physical unit of pressure. One such unit is pascals, abbreviated PA, a unit widely used in the acoustics community. Acoustic pressure amplitudes can range from the 100,000ths to the 100,000s in pascals. Because of the wide range of amplitudes encountered when measuring pressure, it has become convenient and customary to plot the pressure data on the more compact logarithmic scale. On this scale, the unit is the decibel, abbreviated dB, and now instead of plotting the acoustic pressure, you plot the sound pressure level. The decibel values shown here correspond to measurements in the air. The equation for converting pressure to sound pressure level, abbreviated SPL, is SPL equals 10 log P over P ref squared. In this equation, P is a time averaged pressure, and P ref is the reference pressure, a quantity that depends on the medium in which the sound wave is propagating. In water, P ref equals 1 times 10 to the negative 6 pascals, which equals 1 micropascal. In air, P ref equals 20 micropascals. This is the pressure value which represents the threshold of unimpaired human hearing for a 1 kilohertz tone. In other words, the quietest audible sound at that frequency. To get an idea of how pressure and sound pressure level relate, here is an example calculation where air is the supporting medium. We have an acoustic pressure level of 0.036 pascals. The sound pressure level is then calculated to be about 65 decibels. This is the approximate sound pressure level for normal conversation.
That sounds great.
It was fun. It was the first time I've been for a number of years.
Oh, you've been to England often?
Years ago.
Uh-huh.
Some family from England.
Of course.
Here are other examples of sound levels, starting with a very quiet sound and working our way up. A quiet suburban neighborhood will exhibit an average sound level of about 40 decibels. A gas lawnmower 31 meters or 100 feet away will create a sound level of approximately 75 decibels. A diesel truck 15 meters or 50 feet away, traveling at highway speeds, will achieve a maximum level of 85 decibels. A jet aircraft at an altitude of 305 meters or 1,000 feet will create a maximum level of about 90 decibels. The threshold of pain for humans is between 130 and 140 decibels. The sound pressure level is often represented by a capital L. We will now use L to help explain the combining of sound pressure levels. When you need to add sound pressure levels, it is not a simple matter of algebraically adding the numbers. 80 dB plus 80 dB does not equal 160 dB. As explained earlier in the presentation, the decibel scale is logarithmic. Therefore, to combine decibel values, each must be converted to a linear scale, added, and then converted back to a logarithmic scale. Here, L1, L2, up to Ln represent the n sound levels that are to be combined. For applications requiring only integer decibel accuracy, it's also possible to apply some simple steps to calculate an approximate total sound pressure level. First, find the decibel difference between two sound pressure levels. You then add an adjustment factor to the higher of the two sound pressure levels. If the decibel difference is 0 or 1, then you add 3 dB. 2 or 3, you add 2 dB. And between or equal to 4 and 9, you add 1 dB. If the difference is 10 decibels or greater, you can safely ignore the lower level source. Under these conditions, the higher level source is said to mask the lower one. Here's an example combining three sound pressure levels. The typical procedure is to combine the smallest values first, then work your way up. So we start by combining the 80 decibel levels. Their difference is 0, so we add 3 dB to 80 dB to get 83 decibels. Then the difference of 83 dB and 90 dB is 7, so we add 1 dB to 90 dB for a grand total of 91 decibels. Now that we understand how to quantify sound, we can move on to its perception. A sound's loudness is a subjective rather than an objective description of noise. It all depends on how the sound is perceived for a particular individual. When researchers determined there was a need to find a relationship between the sound pressure level of a noise and its subjective loudness, several experiments were performed. As a result of extensive human testing, objective descriptors of loudness were constructed and applied to human perception. We can take a look at examples of descriptive changes in perception and their corresponding sound level changes. When the sound pressure level increases or decreases, some humans in a normal living environment can detect a loudness change if the sound pressure level is altered by 3 dB or more. A change of 1 or 2 decibels will usually go unnoticed. A 5 dB change, on the other hand, can easily be detected by most people. Also, sound will be perceived as being twice as loud if the decibel level increases by 10 dB, or will be half as loud if decreased by 10 dB. And it's common to perceive a 20 decibel change as 4 times as loud or 1/4 as loud. Here's an example of a sound becoming twice as loud. We start with the first sound, complex noise. And here's the second sound, the same audio clip, but at a different sound level. The second audio clip should sound twice as loud as the first. There was a 10 decibel difference. Listen to the sounds again. We can also look at human perception of sound according to frequency. Remember from before that the audible sound range for humans is from 20 to 20,000 hertz. This is shown plotted on a logarithmic scale. Even though perfect human hearing lies in this range, we do not hear equally well at all frequencies. Earlier it was stated that human hearing is most sensitive in the range of about 1,000 to 6,300 hertz. To describe sound levels in a manner which closely approximates normal human hearing, the actual sound level measurement is modified by applying A weighting. A weighting is a response function that spans the audible frequency range. This weighting assigns to each frequency a weight that is related to the sensitivity of the ear at that frequency. Frequencies to which the human ear is less sensitive are weighted less than those to which the ear is more sensitive. The A weighting curve emphasizes frequencies in the 1,000 to 6,300 hertz range and de-emphasizes frequencies out of that range. This is the A weighting plot in tabular form for octave bands. For each center frequency shown, a dB adjustment value is given. For example, for the 125 Hz octave band, a negative 16.1 dB adjustment should be applied. The 500 Hz band requires a negative 3.2 dB adjustment. The 1000 Hz band, which can be thought of as the reference frequency for A weighting, has no adjustment, and the 2000 Hz band requires a positive 1.2 dB adjustment in sound pressure level. A sound pressure level with A weighting applied is often stated in units of dBA. The A-weighted sound level is the most widely used measure of environmental noise and is internationally accepted. Noise can be a steady, continuous sound, or it may tend to fluctuate between intensely loud and quieter periods. An example of the latter is the noise produced by road traffic. It peaks with the passage of a heavy truck and will have quiet intervals when there is little or no traffic. Because of the large array of noises and the need to understand them from different perspectives, there are several ways to describe noise. Many noise descriptors are available where each is appropriate for particular circumstances. A general noise descriptor is one we've already spoken about, the A-weighted sound level. The symbol for this descriptor is L sub A. More specific descriptors are the sound exposure level, the maximum sound level, the hourly equivalent sound level, the day-night average sound level, the community noise equivalent level, and the 10 percentile exceeded sound level. While all of these A-weighted noise descriptors can be applied to highway traffic noise, the LAE Q1H and L10 are most often used for traffic noise analysis. LAE Q1H, called the hourly equivalent sound level, is essentially the average A-weighted sound level occurring during a 1-hour period. To illustrate the equivalent sound level, we are first showing you the sound pressure level recorded at one location over time. This time history reveals peaks and dips caused by loud and quiet sounds during the time period. Now applying the LAE Q1H noise descriptor, the sound pressure level averages and the plot flattens out. This sound descriptor should be applied to continuous sounds, such as relatively dense highway traffic. The other noise descriptor we will discuss is L10, the A-weighted 10 percentile exceeded sound level. It's the sound pressure level exceeded 10% of a specific time period. Here's an example. Say 50 samples were taken during a period of time. You extract the highest 10% of the sound pressure levels, which in this case would be 5 samples. The 5th highest sound pressure level is the 10 percentile exceeded sound level. In the first part of this video, we discussed the basics of acoustics and reviewed some common noise descriptors which can be applied to highway traffic noise. Now we're going to move on to the acoustics involved in highway traffic noise. This includes the noise source, or the vehicles driving on the highway, the receiver of the noise, or the people in nearby communities, and the propagation path of the sound as it travels from the source to the receiver. Let's first talk about the sound source. We'll describe 2 basic sound source types and the relationship to highway traffic noise. A point source is defined as a source that's essentially concentrated at a single point from which noise propagates outward in all directions. In other words, sound radiates spherically from a point source. The sound levels measured from a point source decrease at a rate of 6 dB per doubling of distance. This is a decrease due to spherical spreading. A line source radiates sound cylindrically. It can be composed of multiple point sources arranged on a line located at a perpendicular distance relative to the observer. The sound levels measured from a line source decrease at a rate of 3 dB per doubling of distance. This is a decrease due to cylindrical spreading.